The acid-catalyzed hydration of an alkene is a reaction that adds water across the pi bond of the alkene. So we start with an alkene, and overall we have added a hydrogen to the end carbon atom and an alcohol to the second carbon atom, or overall an equivalent of water, giving us the product of an alcohol. Like most reactions that go through a carbocation intermediate, the hydrogen adds to the least substituted carbon atom of the alkene. So we can also say that this reaction follows Markovnikov's rule. Markovnikov's rule just tells us that the hydrogen adds to that least substituted carbon. It doesn't explain why. Why is to go through the more stable, more substituted carbocation. So let's take a look at the entire mechanism. So we have our alkene, and the first thing that happens is that this alkene reacts with the acid. So your alkene is a nucleophile. The hydrogen atom of that acid is an electrophile. So they react, so we're forming a bond between that hydrogen atom and this end carbon, and we are breaking this bond between the hydrogen and the oxygen. So the product here is a secondary carbocation. We form the secondary carbocation because the alternative would be a primary carbocation, which would be less stable. After you form that secondary carbocation, there's no way for this to rearrange and become more stable, so it doesn't. The nucleophile then at this point will attack, and the nucleophile will be the water. So we are forming a new bond between this oxygen and this carbon. So what we have at this stage is something that looks pretty close to the product that we have drawn up here, but it has an extra hydrogen. So what we need to do here is neutralize this to get to the neutral alcohol product. So we need something that can remove a hydrogen. In other words, we need a base. If we are in aqueous acid solution, that means we probably have a small concentration of H3O+, right? It's a dilute acid, something like dilute sulfuric acid. So we have a small concentration of the hydronium ion, and then the rest of the solution is water. So we can use water as a nucleophile, like we did here. Water can also act as a base, like it is going to do in the next step of this reaction. So water can act as a base, and it will remove this acidic hydrogen atom to give the neutral alcohol product. And in this step, we're also generating H3O+, which was the acid catalyst of the reaction. So if you remember back to general chemistry, a catalyst is not consumed in the reaction. So we saw it used in the first step, and we saw that the acid catalyst was regenerated in this last step. Don't be alarmed seeing two water molecules playing a role in this reaction. This is a solution that is aqueous. There is a ton of water around. It is normal to see the water acting as a nucleophile or also acting as a base to do a proton transfer step. Okay, let's take a look at another example. I want to show you one where the carbocation could rearrange. So I'm going to draw this simple little alkene, and we'll show this reacting with H3O+. So there is the H3O+, so the pi bond attacks the hydrogen, and we break the hydrogen-oxygen bond. We'll put the hydrogen on the less substituted carbon atom to get the more substituted carbocation, which is a secondary carbocation. And whenever we have a carbocation intermediate, look at it closely, make sure that it is the most stable carbocation, and look to see if it can possibly rearrange. In this case, the secondary carbocation, there is a tertiary carbon next door. We do have a hydrogen attached to that tertiary carbon that can shift. So a 1,2 hydride shift to form a tertiary carbocation. Right, so we've moved the hydrogen here, which gets rid of the positive charge. It's taking electrons away from that tertiary carbon, so that's why we end up with the positive charge on the tertiary carbon. And then after that forms, we can have a step like this one where water comes in and acts as a nucleophile. So we have a structure here where the water has attached to the tertiary carbocation. It looks like a protonated alcohol. So what we're going to do next is we're going to use another equivalent of water. Remember, it's the solvent of the reaction. We have 1 million or more fold excess of water, so don't worry about seeing it again. So water here can act as a base. Pull off one of those 2 protons and give the tertiary alcohol as the major product of this reaction.